Okay, so here's Van Morrison's suggestion for how to convert this starting material into butane acid. So it wants us first of all to name compound A. So you can see that we have a chain of 1, 2, 3, 4, which gives us bute. And it's unsaturated, it's got an alkene group in it, so it's ene rather than an. So we're going to put the ene in there and we'll leave a gap for the number to indicate where it is. But it's also an alcohol, and so we have ol as well. So it's going to be bute-ene-ol, and we've just left the gap for the numbers. So ol comes at the end, and so that gets priority in terms of keeping the number as low as possible. So that carbon is going to be 1, 2, 3, 4 is how we're going to number the carbons in the chain. So it's 1 ol, and the alkene group is between 3 and 4, but you quote the lower number, so it's bute 3-ene 1 ol is the name of that compound. So then the question is, well, how could we turn that alkene group in compound A into the alcohol group that we have in compound B? And you can see that that's an addition reaction. So that's part of the answer. That's the type of reaction that we want, is an addition reaction. And what we need to add is OH to this end and hydrogen to that end. So overall we're adding H2O, and you just need to learn that the way you achieve that is that you need steam, so not just water but specifically steam, and you need a phosphoric acid catalyst. And that's the standard technique that you use for adding H2O across an alkene group to make an alcohol. And then in part 3 we come to this issue that yes, you could do that, but as Bob Dylan points out to him, because Bob Dylan's obviously somebody who's studied Markovnikov, this is not a very good way of doing it, because when you add across that double bond there, you're going to get 2 possible intermediates. So when you add water, you add first H plus and then in effect OH minus. So you're going to get 2 possible intermediates. This one, where we've added the hydrogen to that end and therefore got the positive charge there, or this one, where we've added the hydrogen to this end and therefore got the positive charge here. So 2 possible intermediates, and that one will then, in the second step, the OH minus will add on to there to give you this product, which is not the one you want, or this product, which is the one you want. And the problem that Bob has spotted is that this is a secondary carbocation, but this is a primary one. And we know that secondary carbocations are more stable than primary ones, and therefore will be formed more easily. So this is the more stable carbocation, it'll be formed more easily, and that will therefore lead to the major product, which is not the one we want. And that means that we're only going to get a relatively small amount of this. And the way you can quantify that is through the percentage yield. Okay, because if we just wrote the equation, making this the product, it would look great. And we would calculate that for each mole of that, we would theoretically get a mole of this. But then when we did the experiment, because of this problem, we would actually get only a small fraction of that, and that would be quantified as a low percentage yield. Okay, so in part B, Van has a go anyway, and this is what happens. So he takes 2 grams of this, reacts it with excess steam, and he gets 0.8 grams of the product he was hoping for. So we've got to work out what that represents in terms of percentage yield. So as always, can't work directly with masses, so the first step is to turn those into moles. Okay, so we get moles is mass over mR. which is 2.0 over 72.0 is the MR of that compound, which comes to 0.02778 moles. So that's what he had to start with. So he would have been hoping to get a number close to that for his moles of product. But we can work out what he actually got. Moles is mass over MR again, which is 0.80. And the MR of this is obviously different because it's a different compound. This one adds up to 90.0. And if you work that out, that's 0.008889 moles. Okay, so it's a lot smaller than the number we started with. So basically Bob was right that most of this has got converted into something else, not into the product that Van was hoping for. But we can make that quantitative by calculating the percentage yield is actual moles over theoretical moles times 100. So put these numbers in, that's the actual moles, 0.008889 divided by 0.02778 times 100, and that works out as 32%. Okay, so not a great percentage yield, and the Markovnikov thing is going to be the main reason why. So from a percentage yield point of view, Van's process is pretty catastrophic. But remember, there are always two sides to this coin in terms of the efficiency of processes. Percentage yield wise, not good, but what about atom economy? That's a much better picture, because you can see this is an addition reaction. There's only one product, and since that's the desired product, that gives 100% atom economy. So at least that's not such bad news. So then part C turns to the second step in the synthesis, which is conversion of this diol B into butane dioic acid. So first of all, it wants to know what type of reaction this is. So remember, this is oxidation, because we're adding these extra oxygens into the molecule. It's oxidation of an alcohol, so that's the type of reaction. And it wants to know what the reagents and conditions are for that. So standard alcohol oxidizing reagent is aqueous acidic potassium dichromate. Make sure you learn that whole package, not just the dichromate bit. So aqueous acidic potassium dichromate. And because it's a primary alcohol being oxidized to a carboxylic acid, we have to be very careful about the conditions. It's not enough just to say heat, because remember that primary alcohol has two possible oxidation products. It could be an aldehyde, where that just changes into double bondo, or if you oxidize further, you could get the carboxylic acid. And we want to make sure we go the whole way through to the carboxylic acid. And so the conditions are that you heat under reflux. And that means that you keep heating for a long time without losing your material, because the reflux stops it from escaping through evaporation. And that allows you to keep on oxidizing till you've gone all the way through to that. So that's the reagent and conditions. And then it wants a balanced equation. Now you've got to be careful here, because you've got two primary alcohol groups oxidizing. Now remember, for each of them you need 2 moles of oxidizing agent. So it's 2 moles of oxidizing agent for that one, and another 2 for that one, so 4 moles of oxidizing agent altogether. And each time you make a carboxylic acid group, you produce a water as well. So again, because you're producing 2 carboxylic acid groups, you have 2 waters in your balanced equation. So then in part 2, it wants to know why the atom economy for this reaction is much worse than it was for step 1. Remember, it was 100% there because that was an addition reaction, so there was only one product. In this case, you can see there's more than one product. This equation, of course, is a cheat, because it simplifies the oxidizing agent to that. But even with this, you can see there is another product as well, which is going to be a waste product, and so that's going to take the atom economy down. In reality, it's going to be much worse than that, because remember, you've got this dichromate reacting, which gets converted into chromium, a chromium 3 plus compound, which again is a waste product. So actually the percentage yield will be much lower than 100%, because you're producing the product you want plus other products, and if those other products are not useful, then your percentage yield, sorry, your atom economy is going to be depressed. Part D, clearly you can't do until you have learnt about infrared spectroscopy. So if you haven't got onto that yet, then obviously delay looking at this one until you have. But assuming you've reached that point, what this is a spectrum of a compound which is produced when you try to do this, when you try to oxidize this diol to the dioic acid and get something else. And the infrared here is providing you with a clue as to what that might be. So one possibility would be that one or other of these alcohol groups might not have been oxidized at all, might still have remained unreacted. But that seems not to be the case, because if you look on your data sheet, you find that alcohol OHs give you peaks between about 3,200 and 3,600 wave numbers, which are very obvious peaks. So you would get a peak that looked kind of like that if there were still any OH groups in the molecule. And clearly you haven't got that. So that means that the OH groups have definitely gone. What you do have is this peak, and that peak, if you look at the range spanned by the peak, which is sort of something like that, you can see that fits with a C double bond O peak on your data sheet. So we have got carbonyl groups, and that would be consistent with the carboxylic acid, because of course you've got C double bond O carbonyl groups there. But if you look again in your data sheet, carboxylic acids, in addition to having the C double bond O peak, have a very characteristic OH peak, which is different from an alcohol OH peak. And it's extremely broad. It goes from about 2,500, which would be here somewhere, up to about 3,300. So what you would get would be this huge broad peak that goes right over the top of these sharp CH peaks and gives you something that looks kind of like that. So that's what you would expect if there was still any if we'd managed to make any carboxylic acid peaks, and there's no hint of that. So the infrared evidence says that we've got no alcohol OH peaks, but no carboxylic acid OH peaks either. So where does that leave us? Well, thinking about this reaction, we know that in between primary alcohol and carboxylic acid, we have aldehyde. So a carboxylic acid gets, a primary alcohol, which is RCH2OH, gets oxidized first to an aldehyde, which is CHO, and then to a carboxylic acid. And this aldehyde group contains a carbonyl, so it would give that peak, but it hasn't got any kind of OH peak. So this spectrum is consistent with an aldehyde, but it's not consistent with that or that. So the suggestion would be then, based on the infrared evidence, that this compound X, would have aldehyde groups at both ends. So you would have this. As the identity of compound X. Part 2 then introduces compound Y, and the information that we have to help us identify that is this time based on mass spectrometry rather than infrared. So in mass spectrometry you get these M over Z values, which stands for mass divided by charge, but for practical purposes these equate to the relative masses of ions corresponding either to the whole molecule, which are called a molecular ion, or to fragments of the molecule. They're ions with a positive charge because they have to be in order for the method to work. They need a charge so that they can be accelerated in an electric field, and that's the basis of the method. So what we know in the case of compound Y is that we have major peaks at m over z of 57, 73 and 102. So usually the best thing to do in problems like this is to think about the major peak with the biggest m over z first, because it's usually, at least at A level, a safe assumption that that's the molecular ion peak. And the molecular ion peak corresponds to the whole intact molecule just having lost one electron, so that it's a positive ion, but its mass, because the electron mass is so small, its mass is effectively the same as the MR of the molecule. So that's a good place to start, because if you can narrow things down to a reasonable number of possibilities, you can just try matching the mass of the molecular ion to one of those possibilities. These other ones then come from fragments, and having come up with an initial result as to what you think it is, you can see whether these fragments fit. So we'll see if we can make that approach work. So quite a good way to start here would be to start with butanoic acid, because if we work out the MR of that and add that up, we get 118. So a sensible thing to do is to say, right, it's clearly not that, because we know that it's something which was an impurity that wasn't wanted. But if we look at the relationship between the two, the difference in the MR there of 102 and 118 is 16, which is the mass of one oxygen. So you have to think, right, what could be different from that that differs just by one oxygen? And the obvious possibility is if one of these carboxylic acid groups has indeed been created, but the other one is still at the aldehyde stage. So in other words, if you had this, so at this end it's gone all the way through to the carboxylic acid, but at this end it's still at the aldehyde stage, so that you just have CHO at that end rather than COOH. And comparing those two, you can see the difference is just one oxygen atom, so there would be a mass difference of 16. Okay, so this seems like a very good candidate to be compound Y, both because it has an MR which is consistent with the m over z of the molecular ion peak, but also because, of course, it's a compound that we would expect to be formed in between these two compounds, because you've got to oxidize primary alcohol to an aldehyde before you can go through to the carboxylic acid, so that's expected to be formed somewhere as an intermediate along the way. But we can get further evidence in support of that by seeing if we can explain what these fragment peaks are. So this one, the molecular ion peak, we could write like this, just to spell it out. So that's the fragment, that's the molecular structure, but we just put a bracket around it and put the positive charge outside, so that's what the mass spectrometer actually detects. Now these are again going to be positive ions, but they're going to be missing bits. So the best way to identify what the fragments are is, rather than try to find fragments of this which add up to 73, that's quite a big number, so you can spend a lot of time adding things up to try and see if you can fit that. So a better way forward is to look at the difference. So right, so for this one we'll say, right, we know that the total MR is 102, so if we say 102 minus 73 is equal to 29, what that means is that we can get an ion with a mass of 73 if we can somehow lose 29 from that molecule. So how might that work? Well, 29 can occur in two common ways by adding up combinations of carbon, hydrogen and oxygen. One is CH2CH3, an ethyl group, that adds up to 29, and there isn't one in that molecule, so that doesn't seem to fit. But the other one is CHO, an aldehyde group, because if you add up 12 and 16 and 1, you get 29. So if this molecule were to break here, as it was forming the molecular ion, you could get this, which would be COOH would be intact, CH2, CH2, and then all of that's chopped off, so it would just be that with a positive charge. So just with the aldehyde group gone, we'd take 29 away, and that would account for the peak at 73. So we can do the same thing with 57 and say 102 minus 57 is equal to 45, and 45 is the mass of a carboxylic acid group, COOH. So if the molecule, instead of breaking there, was to break here and just chop off the COOH group but leave the rest of it, then we would get a mass of 57. So that would be CH2, CH2, CHO, plus. Okay, so if we're just chopping off the COOH but leaving the rest, we have CH2, CH2, CHO, and that does indeed add up to 57. So both of the fragment peaks are accounted for, as well as the molecular ion peak, and so that combination gives you very strong evidence that compound Y is indeed that. So part 3 then wants to know what we can do to get a better percentage yield of this, and you can see the problem is that we're getting Y, which was this compound, and we're getting whatever the other one was, and we're getting X, which was this, and both of them are things which haven't been oxidized far enough. Starting from here, we would form these en route to forming that, and we haven't got far enough. So basically what we need to do is to react for a longer time, and the way you do that is use reflux and basically just increase the reflux time to make sure that sufficient time is allowed for complete oxidation of the primary alcohol, not just to the aldehyde stage, but all the way through to the carboxylic acid stage.